Hello, everyone. It's about time to start. You can go ahead and chat me your first and last name. Anybody have any questions before we get started?
I had a question
Yeah, Dylan.
on the online test, the face-to-face test, and then the final, are they all going to be on 17 through 29?
Let me look again, just because I don't like answering such questions off the top of my head. There's a good chance I'll make a mistake, so I'm gonna go check. I'm
I know
looking, and
usually
when
the
I'm
online tests are like every two chapters.
right, that's normally the scenario. Sometimes the last test will cover a couple other chapters, but right now what I've got it set to is there's an online test six that's due April 27th, and that's 17 to 29. And in other words, it's really mostly on 27, 28, and 29, but they're all comprehensive. So that's why I set it that way. And then there's a practice test for the final exam, which is chapter 17 to 29 as well. So yeah, everything's basically 17 to 29. But it's not that I've made an attempt to put a lot of stuff from 17 through 25 in it. It's just a matter of they're all comprehensive. So
Okay, I just want to check.
that makes sense.
Yep.
All right. I was going to make an announcement as well. Uh, I did put those practice tests, the extra credit for the previous test. They're still in week 12, so it looks like a lot of people have taken them. If y'all need more time, I can give you more time, but you definitely need to learn how to do that stuff. So if you don't, please contact me. Let me know that you need more time, and I'll be glad to give you more time. Even if it's you've already got your 100, but you just need more practice, just let me know because all of those things, even though they might not appear in the practice test, they're still fair game because that's they're built on questions that were from the practice test. So just keep that in mind. And I think that's pretty much it that I had to say. But any other questions? All right, looks like you've all went ahead and chatted me your first and last name, so that's good. I'm going to start off by sharing my computer screen for a second because I want to use a diagram here. So right now you're looking at this diagram, and according to conventional current definitions, which is what we use, we imagine positive particles within the conducting wire to flee from the positive terminal of this battery. That means the current is going to run around this way and then go behind the ring and then come out through the center and then go across the front of the ring and then go back behind the ring, come out through the center, go across the front of the ring, go back behind the ring, so on and so forth. So what that means is if we were to grab this little wire right here with our right hand to figure out which way the magnetic field would point, we would have to take and hold our hand like this where our right thumb is pointing to the left, and then we imagine grabbing that wire and poking our hands down basically between the wire and the green ring. So that means the magnetic field is going down in that ring, and therefore you can picture that magnetic field as spiraling around counterclockwise around this iron ring. The iron ring, being a ferromagnetic material or a paramagnetic material, would do the same thing. But basically, what that does is tends to give the magnetic field the ability to stay more within the iron than just going off and depleting to zero. That's sort of the action of what the ferromagnetic and paramagnetic and even diamagnetic material, only diamagnetic material does it in the opposite direction. So in this case, what we've got is a magnetic field that is going around in a counterclockwise way around this ring. Now that's important because initially, when the switch is off, when the switch is open like that, there's no magnetic field whatsoever. So Faraday's law says the induced EMF is equal to negative N, where N is the number of turns, times d phi b over dt, where phi b is the magnetic flux. So that negative sign we interpret as Lenz's law, and Lenz's law says that an induced current will be created in an attempt to oppose the change in flux. So since this loop over here called Y, see that coil of wire Y? Since that coil initially had no magnetic field going through it at all when the switch was open, and then all of a sudden it had a magnetic field going through it in a counterclockwise direction like this, then it's going to try to oppose that change in flux. The flux is increasing. That's what the change is. So it's going to try to decrease the flux. The way it can decrease the flux is it can create an EMF, which of course creates a current. And when you create a current, you create a magnetic field. Since we're trying to oppose the change in flux and the flux is increasing once we turn the switch on, then the induced EMF in the Y coil is going to create a magnetic field pointing the opposite direction. In other words, the Y coil is going to try to create a magnetic field in the clockwise direction. Because of that, that means the magnetic field, if you were to grab this bottom wire right here, notice the front of it is in front of the green loop. I'm going to grab that so that my fingers go down through the middle because that's the direction of the magnetic field that we're trying to induce. The magnetic field that we're trying to induce is trying to decrease the flux. The flux had the magnetic field going counterclockwise, so we're trying to create a clockwise magnetic field. And to do that, you grab that right wire, you poke your fingers between the coil and the green ring, your fingers of your right hand, and you'll see that that means the current in that bottom wire will be going down and to the left. So that current in that bottom loop is going to go down through the middle of the ring and then back behind the ring, and it's going to enter in the right terminal of the galvanometer and then come out the left terminal of the galvanometer. Now that all depends on what the markings are on this galvanometer. But if, for instance, this is the red side, then this would deviate to the plus, and that would mean this is also the black side, so it would deviate to the plus. If we were going the other way, then it would deviate to the left side. But in this case, that's what it's going to be. So what I need you guys to do is think about that or take the time to write down Lenz's law in a wording that you're familiar with, or that a wording that you understand. And every time you see a changing magnetic flux, I want you first to establish whether or not it's changing. If it is, then you want to say, is it increasing or decreasing? And once you decide that, then you want to say, okay, well, how am I going to create a current in some other part to oppose that change in flux and then predict the direction of the induced current? Okay. The induced EMF doesn't help that much because you need an induced EMF to create a current, but it's only the current that we understand as creating a magnetic field. You can't just jump from voltage to magnetic field until you get a little bit more familiarity with it. So that's what your thought process should be. And every time you see a diagram in this chapter, you need to start thinking that way because this is a fundamental question that's extremely important. As I mentioned last time, it's so important that I literally put that in my interviews and anybody I'm hiring for a physics or engineering position. And if they can't answer the question, which way would be an induced current, then they're not getting the job. I'm going to not recommend them for that. So it's that important. It's that critical. It's that simple. It's that everything. So you guys got to know this. So again, if I switch this switch closed, initially there was no magnetic field going through coil Y nor through coil X. But as soon as I switch that closed, then a current will go down this way. It'll go behind the green ring and then come out the middle and then go across the front of the green ring and then go back behind it from the outside and then come back in from the inside, go back in front of it. And if you grab any one of those coils of wire in X, such as your such as your right thumb is pointing to the left, that will show you that that is the actual current direction. And your fingers going through the middle of that coil of wire suggests that the magnetic field should go in a counterclockwise direction around this ring. Now, originally the switch was open, so there was no flux through Y. Now there is a flux, so that means the flux is increasing. When the flux is increasing, an induced EMF and therefore an induced current will be created to oppose that change. So there's going to be a induced current that's going to try to make the flux decrease. The way it makes the flux decrease is it basically creates a magnetic field in the opposite direction. If it was trying to make the flux increase, it would create a magnetic field in the same direction. So in this case, we want a magnetic field that goes clockwise. And to see that, I could either grab that top wire with my right hand, make sure my fingers go between it and the metal green ring, okay, and point down because that's what makes it going clockwise. And when I see that, then I see that my right thumb is pointing to the left, and therefore the current that needs to be induced would have to go to the left and then go inside the ring and go back behind it through the middle of the ring, and then it'll come out again on the outside of the ring, go across the front, and then go back into the board, into the screen, and then go back behind it, come back out in front again from the outside, and so on and so forth. So all of that tells us the current will be going in the right side of the galvanometer and out the left side of the galvanometer. Now, we can also do double duty. So imagine for a second that the switch is already closed and we're going to actually open the switch. So if we imagine the switch is already closed, then we know what's happening. The switch being closed tells us that there's going to be a magnetic field going in a counterclockwise direction around this iron ring. As soon as we turn that off, the magnetic field is going to decrease, go to zero more or less, and that means the flux through Y is decreasing. So, according to Lenz's law, induced EMF will be created, and therefore an induced current will be created to oppose that change in flux. In this case, the current that's going to be induced is going to try to create a magnetic field to replace the previously existing magnetic field, which was counterclockwise. So if I grab this bottom loop of wire in Y, this time I want my fingers to go behind the wire and in front of the ring, but I want them to come up because that would produce a counterclockwise magnetic field. So in doing that, what I see is my right thumb is now pointing to the right, and that means the current will go to the right in this wire, and then outside of the ring, it'll go back into the page, and then it'll go to the left behind the ring, and then it'll come out of the page on the inside of the circle, and then go across the front. So basically, what you're seeing is now the current will enter the left terminal of the galvanometer and come out the right terminal of it. So that's Lenz's law. That's Faraday's law, and that's the single most important concept I'd say from this whole semester. Okay, it's that important. So you guys need to work on that. We're going to see it over and over again. Here's another case. You can imagine we're jamming this magnetic or excuse me, this magnet up towards the ring. You can imagine initially that the magnet was way down here at the bottom of the screen. And that the reason why I'm saying that is because then the magnetic field will not be able to reach far enough to have any magnetic field lines going through this ring of wire. But what we're going to imagine is it slowly or fastly, either one, approaching the ring of wire from the galvanometer, but from below. And remember, I told you magnetic fields are like old people. They exit the north and enter the south. So that's why these arrows are all pointing up. So what you see is initially there was no flux through the middle. That's when the magnet was really far away down below. And now all of a sudden there's a flux through the middle of the coil. As Lenz's law says, a current will be induced to oppose the change in flux. Well, what's the change in flux? The change in flux in part A is that the flux was zero and now it's increasing. So the flux is increasing and the induced current is going to be induced in such a way to decrease the flux. That means it's going to create a magnetic field pointing the opposite direction. So we got to create a magnetic field pointing down because these north arrows point up. So I'm going to take my fingers of my right hand and poke them through the hole in the middle of that loop of current connected to the galvanometer. And now I'm going to grab that front part of the wire. And what I see is, in order for the magnetic field to go down through the middle, then the current in that front wire must go to the left. So that tells us that, in fact, current will be entering the left-hand side of the galvanometer and exiting the right-hand side. And notice that's how they have the eyes drawn. Now, if you were pulling it out, which is what you're doing here, then what we had is, initially there was a flux going up through, there's a magnetic field going up through the ring, and that meant there was a significant magnetic flux. But as you pull it down, that flux is going to decrease because the magnetic field is going to get weaker and weaker and weaker. So Lenz's law says that an induced current will be created so that it can oppose that change. Well, since the flux is decreasing, it's going to try to increase the flux, and it's going to do so by creating a magnetic field pointing up through the middle. So if I grab that front part of the wire by taking my right fingers and poking it through the hole in that circuit, in that circle of wire, that would indicate a magnetic field pointing up, which is what it currently is, and that's what we want. So when I do that, now I can coil my paws. I can coil my palm in such a way that I can now grab the front part of the wire, and I see my right thumb is now pointing to the right, and that suggests the current will go around this way, and that means it's going in the right terminal of the galvanometer and out the left terminal. So evidently, when it goes in the right and out the left, that deflects to the negative side. But when it goes in the left and out the right, that deflects to the positive side. So that's how you know that. Now, if you, on the other hand, just hold a magnet still in that loop, there's no magnetic flux change. There is a magnetic flux, but it's not changing. If you move it just a little bit, then it's flux changing. But if you just hold it perfectly still, it's flux, but it's not changing. Okay. So that's some of the tricks we've got to be able to get used to and be able to do at the drop of a hat. So I recommend you looking through these figures in this chapter repeatedly and predicting it before reading it. Like, try to cover up as much of the words as you can every time you see a figure, and then see if you can figure out which way the induced current will be. And then check by reading the book and see if you got it right. When you're done with that, if you still don't have enough, then what you want to do is go over here to chapter 29. And at the end, you're going to see there's problems. You might even find some in these questions and these misconceptual questions, but I generally look for the problems because that's, back in my day when we went to school, that was the only problems you had, and you were only fortunate enough to have answers, and it was literally just an answer, not a solution for the problems, and it was only the odd ones. So if you click on problems here, you'll see a bunch of little things, diagrams that look like stuff. Like this one right here is a picture of a loop of wire, and it has part of the loop of wire submerged in a magnetic field that seems to be going into the page. So if you were to consider pushing the wire to the right, would the flux increase or decrease? And if so, what direction would the induced magnetic field, or excuse me, would the induced current act? In this case, it's saying the rectangular loop shown in 2946 is pushed into the magnetic field, which points inward. In what direction is induced current? So this one, they're literally telling you, hey, I'm pushing this to the right. Okay. So what you see is, right now there's flux given by the strength of the magnetic field times this small area right here. But as this thing moves to the right, the area is getting bigger and bigger and bigger. And since the area is getting bigger, that means the flux is increasing. Since the flux is increasing, the induced current will try to oppose that increasing flux by creating a magnetic field pointing in the opposite way. So if we imagine a magnetic field pointing out of the page, all we do is take our right tips of our fingers and imagine poking them through the middle of that coil out towards us. Now we can either use our thumb, which is down at the bottom, and grab the wire at the bottom, and that'll tell us which direction the current in the bottom's going. Or we can turn it this way, and that'll tell us which direction the current in the right side is going. Or we can turn it this way, and that'll tell us which way the current in the top is going, all of which point to the same thing. Specifically, the induced current will be in a counterclockwise direction. So every time you see a diagram like that, you can predict it and guess. Here's some more diagrams. I highly recommend you go back and do this over and over and over again. That's going to be a fundamental question that you're going to be asked a lot. So, anybody have any questions on that Lenz's law interpretation? All right. So now that we have that, I've already given you the mathematical side of it to some extent. I've told you basically what the equation was and so on. In fact, what the equation was, ooh, it might be helpful if I have my Apple Pencil. Woo, there it is. All right. So I'm going to go ahead and stop sharing the screen right now, and I'm going to go back to sharing my iPad screen. And to do so, I'm going to do share more iPhone, iPad via AirPlay. Now I'm checking this. Looks like it's coming up. All right. Should be up any second now. Okay, let me try again. Why is it not? Whoa, why is it going down here? Oh, I pushed the wrong button. That's not it. Yeah, that's
What
the one.
actually causes the induced current when the magnet gets near the wire? Is it the magnetic field affecting like the electrons instantly? Or
It seems to be sort of a conservation of energy because what we can do is we can show that if it actually induced a current in the opposite way, then it would be the equivalent of creating a perpetual motion type machine. So it would literally violate like the second law of thermodynamics. So it's free energy. But that's basically it. Is it does seem to, because magnetic fields behave the way they do, it does seem to create currents and moving. If any electrons or any charged particles have a velocity that's not zero, then the magnetic field is going to compel them to move. But at the deeper level, we really I can't answer it too terribly much. All I can tell you is that's the only way that you can have an electric field and a magnetic field existing is when they behave this way. Uh, we didn't know that a priori. We just knew that we were working out this thing, and for a while it looked like there was something that was related to charges that turned out to be the electric field, and then there turned out to be this thing that affected charges, but it affected them perpendicular to their motion, which was kind of odd. Ultimately, we figured out that was magnetic fields, and we ultimately, of course, figured out that that only happens if the charged particles are moving. So at the end of the day, there's a lot about physics that we don't know the exactly why the laws of physics are the way they are. We just know that they are. And that's sort of what this is. That there's a probably a higher level thought process that you could go through, but I'm not ready to explain it at this point, and I'm not even sure I've ever learned it, much less be able to explain it well enough for you guys to understand if I understood it. So to date, I would say that just happens to be the way it is, and I can't really tell you more than it's the only way that it would be internally consistent with the electric field and the magnetic field and the laws of relativity. That's one of the interesting things about Maxwell's equations. Maxwell's equations were automatically relativistically correct, so they were completely consistent with special relativity, and that's why Einstein used the ideas of electricity and magnetism to discover the special theory of relativity. In fact, his first paper on special relativity was on the electrodynamics of moving bodies because he specifically saw the problems. So I can't give you more than that, but hopefully that's enough for right now. But it's a good question. It's exactly the kind of questions we like to think about. It's just sometimes we can't answer it. Like I don't know why space bends as a result of gravity, or excuse me, as a result of mass, and then that imitates gravity. But that's the case for a lot of laws of physics. We certainly don't understand anything about why quantum mechanics is the way it is. It's that's a crazy world, way more crazy than relativity, and even way more crazy than, especially than relativistic, or excuse me, than electrodynamics or classical mechanics. Anything else? Anybody else? I'm sorry I couldn't give you a better answer. All right. So let me tell you what Faraday's law is. Initially, Faraday's law says the induced EMF is equal to negative d phi b over dt. But as I said, it turns out that if you have a changing magnetic flux through a through a single loop of wire, you get an EMF given by this equation. But if you have it through n loops of wire, then you have an uh, induced EMF given by n times that d phi b dt. And we often will replace the E with the closed integral of E dot dl. That is a precursor of what to understand about what Maxwell's equations are. Maxwell's equations in general are can be looked at as integral equations, which is the way we've mostly been doing them, or as differential equations, which is the way you'll do it in a more mature class. So if you go to a electrodynamics course that's 2 semesters, nothing but electrodynamics, you're going to start off with you're going to use the integral forms like we're doing as well because that's a touchstone, and they'll show you even neater, more advanced ways, but then you'll jump right into the differential equations. And for instance, Gauss's law, which was the closed integral of E dot dA is equal to Q enclosed over epsilon naught, that actually is going to become del dot D, where D is some kind of field that's slightly different from the electric field in material, but that's equal to rho. And it differs from units to units, where rho is that charge density. So that is the differential equation equivalent of that equation to the left. So that's ultimately what it's going to become. Now that we have all that, I want to also say, remember Ohm's law is in place. So Ohm's law was V equals IR, and E, the EMF, the electromotive force, is the same thing as V. So if you ever have to calculate other than the voltage, you actually have to calculate the current or something like that, then you need to remember that you can go ahead and say Faraday's law is not just E is equal to negative N d phi b over dt. It actually becomes I times R is equal to negative N d phi b over dt. And I mentioned this last time, but if you're taking Faraday's law and you're taking it as an equation and sticking it in another equation, then you absolutely have to include that negative. But a lot of the calculations we do, you're just looking for magnitudes, and the negative is sort of a reminder to apply Lenz's law, meaning that the induced EMF is going to oppose the change in flux. So you pretty much don't use the negative when you're doing quick calculations like what's the induced current or what's the induced voltage or something like that. So with that in mind, let me move through some examples to give you a little bit more experience. Whoa, I just jumped a whole lot of pages all at once and didn't mean to. And I don't know how I did, but that's awesome. Okay. I keep the book open on the side so I can go back and forth between examples that I'm doing and stuff like that. So we should remind you that just like flux in the electric case, we had the electric flux, which we didn't put a subscript e on it before, uh, but we have to now. That was the integral of E dot dA. Now, in Gauss's law, we had to have the closed integral, so we wrote that little circle on it because it turns out Gauss's law only works for a closed surface. It's still, it's true, but it's only true for a closed surface. Now, similarly, we have a magnetic flux, and we're going to subscript that B, and that turns out to just be B dot dA. So just like we had before, we're going to imagine a area element dA, and the area inside of that differential area element is the magnitude of the vector itself, and the vector lies perpendicular to the differential area element. So you might, for instance, imagine this little vanilla card as like our little piece of rectangle. It would be represented by a vector that points either that way or this way, perfectly perpendicular to the card. Okay. So it's either going to point that way or this way. But the main thing is it is perpendicular to it, and its magnitude is going to be equal to the magnitude of the area inside this room or inside that card. So just like we did with Gauss's law, we had a particular way that we could define dA so that it wasn't arbitrary. It had a definite out way that dA pointed, but the only way we were able to do that is when we were dealing with a closed surface, and we defined the form to be such that the dA always points from inside out. So that way, there's no arbitrariness. It's not either or this way or that way. It's only this way if you are talking about a closed surface. But once you're not talking about a closed surface, you're back to the arbitrariness of it. So that's what our magnetic flux is. Remember, the way that works is if the magnetic field is a constant, then you can sort of pull that b out in front of the integral, and then you just have the integral of dA, which is the area. So if the magnetic field is a constant all over the whole area, then this just becomes phi b is just equal to b times area. However, if the magnetic field changes at different places, then you have to divide the surface up into smaller and smaller shapes, normally rectangles, but you might use polar coordinates or spherical coordinates, in which case it'd be some other shapes. But the main thing is you'd shrink them down infinitesimally small so that you'd got them so small that the magnetic field wouldn't change in magnitude or relative direction anywhere over the entire dA. If you found that you divided it up into, say, individual millimeter by millimeter rectangles, and you still found that the magnetic field varied over that 1 millimeter by 1 millimeter rectangle, then you'd have to drop it down to a zero point 0.1 by zero point 0.1 millimeter rectangle, or maybe smaller still, maybe 0.01 by zero point zero 0.01 millimeter, or 0.02 by zero point zero 0.02, or something like that. But that's the main thing. Now, in addition to that, it doesn't just matter whether the magnitude is changing because of the dot product. It also matters whether the direction's changing, because basically you have to take the cosine of the angle between the magnetic field vector and the dA vector when they're tail to tail. That cosine can be thought of as choosing the component of the magnetic field that happens to be parallel to the dA vector, or you can think of it as choosing the component of the differential area vector that happens to be parallel to B. Either one doesn't matter, but the main thing is it picks off that component that's parallel to the dA. And remember, the dA is technically perpendicular to the actual area that we're talking about. So, with that in mind, let's do a simple little conceptual example. Example 29.1 says determining flux, and they have a sort of neat little figure here. What we have is, let's say, we've got a big rectangle right here. And this is a big rectangle. And then somewhere within that big rectangle is a smaller rectangle. But in the smaller rectangle, there is a magnetic field that is everywhere in that rectangle. And this area we're going to call A2, and this area we're going to call A1. And this is conceptual example 29.1. Now, in this example, they're asking, what is the flux? Or specifically, what is the magnetic flux? So what's really happening here is we're integrating over this whole surface. We're doing phi b is equal to the integral of b dot dA over that entire surface. So if we choose our little dA, for instance, to be this little rectangle, that's the differential area element, but the differential area vector would be pointing straight up or straight down. Again, this isn't a closed surface, so it's arbitrary whether it points straight up or straight down. But what we do know is for this little rectangle, b is equal to 0. And then for this little rectangle, b is equal to 0 too. And this little rectangle, b is equal to 0. So what you see is all these little areas, when you integrate it, you're just going to get b equal to 0 times whatever the area is. So that gives you 0. So that ultimately you're able to reach the conclusion that the magnetic field, or excuse me, the magnetic flux is just going to be B times A2 because only when we're working in this little area is the magnetic field not zero. Anybody have any questions on that? Okay. So let's look at example 29.2. Example 29.2 says a square loop of wire of side L equal 5.0 centimeters is in a uniform magnetic field B equals 0.16 Tesla. What is the magnetic flux in the loop? So we've got L equals 5.0 centimeters and B is equal to 0.16 Tesla. It's uniform, and they tell you they want to know what is the magnetic flux. So they're saying phi b equals question mark, and then part A, they're asking when B is perpendicular to the face of the loop. When B is perpendicular to the face of the loop. So in this case, we're imagining just a loop of area A, a square loop basically. And what we're saying is, let's imagine this is our loop and it's L by L. And then if you imagine a line perpendicular to that surface, that would be the direction of the magnetic field. So we're seeing B is that case, and that's right at a right angle to that, and that's a right angle to that as well. So in that case, we're going to get phi B is equal to 0.16 Tesla times 5.0 times 10 to the negative 2 meters times 5.0 times 10 to the negative 2 meters times the cosine of the angle between the area vector and the B vector. And that angle, of course, is 0 degrees. And the cosine of 0 is, of course, 1. So now I'm going to take 0.16 times 0.05 times 0.05, and that's going to give me 4.00 carrying one extra digit times 10 to the negative fourth, and that is Tesla meter squared. So uh, that's the actual flux, but we actually have a unit that we use for that, and that unit is called the Weber. So phi b is equal to 4.00 times 10 to the negative 4 Tesla meter squared, which equals 4.00 times 10 to the negative 4 Webers. So that's another unit you need to know. And the Weber is a Tesla meter squared. For part B, they ask when B is at an angle of 30 degrees to the area A of the loop. But in this case, they're saying area A and they drew a vector. So for part B, we say phi B is equal to question mark when B is at 30 degrees from being parallel. I should say it like this. I should say 30 degrees from the A vector. Okay, so when they're referencing it with respect to the area vector, we know the area vector is perpendicular, and the complete, in other words, the most complete flux occurs when the magnetic field is parallel to that area vector. And in this case, they're saying it's 30 degrees from it. So we know what it is when it's completely full. It's full 4 times 10 to the 4th. So in this case, phi b is going to be 4.00. Oops, that last zero looks like a 6. 4.00 times 10 to the negative fourth Webers times the cosine of 30 degrees. So phi b in this case is 4 times, oops, can't do it that way, 0.0004 times cosine 30 degrees, and I'm still in degree mode. So this gives me 3.0, or excuse me, 3.46 times 10 to the negative fourth Webers. That's our flux for that particular case. And then for part C, they said, what is the magnitude of the average current in the loop if the resistance of the wire is 0.12 ohms, or excuse me, 0.012 ohms while it is rotated from position A to position B, or actually from position B to position A in 0.14 seconds. So this one, we don't really have the room to do it here, but I will flip to the next side and say for part C, we want uh, I induced if it goes from B to A in delta T equals 0.0, or excuse me, 0.14 seconds, and R is equal to 0.012 ohms. So what we're using here is E is equal to, in this case, we were never told that it was multiple loops, it's just a single loop. So in this case, E is negative d phi b over dt, which is approximately equal to delta phi b over delta t, like that. And we also know that we can write that as approximately equal to I induced times R. So that's really what we're looking for. We'll say I induced is in fact equal to negative 1 over R times delta phi B over delta t. And remember, deltas always mean final minus initial. I'm going to keep the negative sign on here. It's probably going to work out that it just comes out positive, but if it didn't, I'd just throw the I'd throw the negative away. So I'm just going to keep it right here to see what happens. But remember, the deltas mean final minus initial, and they're saying the B is the initial and the final is the A. So from position B, which is what we found, the 30-degree one, to position A. So the A was 4.00 times 10 to the negative fourth Webers minus 3.46 times 10 to the negative fourth Webers, like that. And then all of that will be divided by R, which is 0.012 ohms, and then delta T, which is 0.14 seconds. And it turns out that a Weber per second ohm is in fact an ampere. So all I have to do now is say 4 times 10 to the negative fourth minus 3.46 times 10 to the negative fourth gives me 5.4 times 10 to the negative fifth. And then I divide that by that actually did come out to be negative. That's 5.40 times 10 to the negative 1, 2, 3, 4, 5, 10 to the negative fifth Webers over 0.012, 0.012, ooh, times 0.14, and that's going to be 1.68 times 10 to the negative 3, and that's ohm seconds. So I induced is going to be, I'm just going to drop the negative because there's no need for it, 0.000054 divided by 0.00168. And that gives me 0.0321 amps. So that's how that works. And if you wanted to think about what it actually did, we said it went from B to A. So the A was the final, and that was the case where it was perpendicular. So if we looked at that, we might say, okay, the ring was like this, or the loop was like this, and the magnetic field and the area vector were parallel. So this is the magnetic field vector, and this would be the area vector. And then it turned 30 degrees. So we might say that instead it now looks like this, where again the magnetic field is pointing to the right, but the area vector is now 30 degrees. So if that happened, what we did is we had a magnetic flux that was quite large, but when we turned it to 30 degrees, it got smaller. And since it got smaller, Lenz's law says an induced current will happen, and that induced current will be in such a direction to oppose the change in flux. So what's going to happen is a current is going to be induced in this loop to try to strengthen the magnetic field. So that means a current that's going to point in the same direction as the magnetic field that we had, and that means the induced current is going to have to be, using your right hand rule, it's going to have to go this way. Because notice if you grab that top wire such that your fingers point out through from behind, like the magnetic field was, then your right thumb points like the way I have the arrow drawn here. So this induced current is not only 32 milliamps, but it points in that direction. So I would call that in the counterclockwise direction. Any questions on that? All right. A current produced by an induced EMF creates a magnetic field that opposes the original change in magnetic flux. That's one of the ways they've worded it. Another way they worded it is an induced EMF is always induced in a direction that opposes the original change in flux that caused it. They have another couple of examples where they're taking magnets and shoving them into rings. They have another example where they have a loop of many, many wires like this, and it's in a magnetic field, and then they stretch it so that the actual area shrinks. Since the area is shrinking, that means the flux is shrinking because the magnetic field strength didn't change, the magnetic field direction didn't change, and the A vector didn't change in terms of direction, anyways. But the A vector length definitely got shorter. So, because of that, an induced current will be created to try to create that magnetic field even stronger, and that's going to produce it in the diagram. It'll produce a clockwise current. So that's another figure 29.6, that you'd want to look at and see if you can predict it. Now, conceptual example 29.3, induction stove. It says in an induction stove, figure 29.8, an AC current exists in a coil that is the burner. A burner never gets hot. Why will it heat a metal pan, usually iron, but not a glass container? and they show you a person laying their hand actually on the burner as well. The reason that is basically what you have is a bunch of loops of wire with a current going through it, and it's an AC current, and that AC current is changing constantly. So you at 1 second you got a magnetic field up, and then actually 1/2 of a 60th of a second later it's pointing down, and then 1/2 of a 60th of a second later it's pointing up, and so on and so forth. That's happening inside of the bottom of the pot too, and the pot is made of a conductor, so it's going to generate a current that goes around this way and then around that way and then around this way and then around that way. And when current goes through a conductor, P equals IV tells us that energy is actually dissipated per unit time, and that energy happens to be in the form of heat. Wires get hot when you run current through them, and of course, iron pots get hot when you run current through them as well. And if you stuck your hand there, unless you happen to be, Wolverine or something with some kind of conductive material in your body, then you're not going to feel any current whatsoever, or not very much, anyways. So that's how the induction stove works. That's also how your cell phone chargers work nowadays. You can, in many cases, you can take your cell phone and just lay it on its back on a certain type of charger. And all that charger is it's got a bunch of loops of wire in the back. And then in the back of your phone, it's got a loops of wire as well. So that when you've got AC current going through the loops of wire in the charger, that's changing the magnetic field going through the loop of wire in the back of your phone. So that's generating a current in the back of your phone that can be used to charge a battery. So, any questions on that? Conceptual example 29.4 is another great example. So I'm going to stop sharing the screen for a second and start sharing the screen with the actual examples from the book in it. So just because this example is a particularly good one and I want to make sure you guys follow it. So conceptual example 29.4, practice with Lenz's law. In which direction is the current induced in the circular loop for each situation in figure 29.9? So in part A, it says, notice this rectangle right here. That's supposed to represent the boundaries of where the magnetic field is. And these circles with dots in the middle represent magnetic fields sticking out of the page. So when you're taking this ring right here and pulling it that way, this little part right here doesn't have any magnetic field in it. But as this ring goes further and further and further, a smaller area is actually within the magnetic field. So that means the flux is decreasing. The flux is decreasing not because the magnetic field went down, not because the direction of the magnetic field changed, but because the magnitude of the area through which the magnetic field went shrunk. So magnetic flux decreasing means that an induced current will be created to try to increase the magnetic flux. So we're going to generate a magnetic field pointing out of the page to make up for the lost flux that we had. So if you take your fingers of your right hand and imagine sticking them from behind the ring out towards you, then you can either grab the bottom of the ring and see which way the current goes in the bottom, or you can grab the right side of the ring and see which way the current goes in the right, or you can grab the top and see which way it goes in the top, or you can grab the left and see which way it goes in the left. All of those point to it going this way, which is counterclockwise. So the induced current in part A would be counterclockwise. If you look at part B, what we have is a big ring with magnetic field going into the page. And after some time, that big ring shrinks to the smaller ring. So remember, the integral of B dot dA has three ways of changing. The magnitude of B can change, the magnitude of A can change, or the direction between B and the A vector can change. That's the only three ways to do it. In this case, the area is changing and the area got smaller. So the flux is proportional to B and A and the cosine of the angle between them. So the B staying the same means no change, but the A getting smaller tells us the flux is decreasing. So this is a decreasing flux situation, and Lenz's law tells us that induced current will be created to try to increase the flux. So it's going to try to strengthen that magnetic field that's going into the page. So if I take my right hand and stick my fingers into that inner ring, like this, I can then grab the bottom part of that inner ring with my right hand, and that would suggest that the bottom part has the current going to the left. If I did it with the left part, it would suggest the current goes up. If I did it with the top part, it would suggest the current goes to the right. If I did it to the right part, it would suggest the current goes down. All of that points to the induced current going in the counterclockwise, or excuse me, in that case, it's actually the clockwise direction. For part C, it says the south magnetic pole moving from below up toward the loop. This one's a little more difficult, but remember I told you magnetic fields are like quote unquote elderly people. That means the magnetic field lines exit the North Pole and enter the South Pole. So in this case, the magnetic field's more or less going into the page, but it says the South magnetic pole moving from below up toward the loop. So that means the magnetic field was really far away because the magnet was far away, and that meant there was no flux. And now, as you get closer and closer and closer, there is a flux. So the flux is increasing, and it's increasing such that the magnetic field points in the middle. So Lenz's law says an induced current will be created to oppose that change in flux. That flux is actually increasing, so it's going to try to decrease it by creating a magnetic field in the opposite way. As we said, the magnetic field is pointing in, so it's going to create a magnetic field coming out, and therefore you take your right fingers, pull them right through the middle from behind, the middle of the loop from behind, and you grab that bottom part of the wire, and you see that my right thumb is pointing to the right. So this case is a counterclockwise current being induced. The one in D, actually, it has the magnetic field symmetry of the magnet such that no field lines are actually going to be perpendicular. No component, more or less, of the magnetic field is going to be both perpendicular to the face of the area and going through it. Now, at one side, the magnetic field, like in front of it, the magnetic field points out, and behind it, the magnetic field points in. But right along it, all the magnetic field is going to the right. So there's no flux in it, and the flux isn't increasing or decreasing. So there's no change in flux and no induced current. If you're looking at the last part, part C, we have a magnetic field that points to the left. And right now, the ring is flat, and the area vector would either point at me or away from me. Either way, both cases are perpendicular to the B. And of course, the cosine of 90 degrees is zero. So in this case, you have zero flux. But what they're saying with that little arrow is that ring is rotating this way. Since that ring is rotating this way, it's going from zero flux to inflict a maximum amount of flux with the magnetic field going this way. So the induced current is going to try to oppose that increased flux by creating a magnetic field to the right as this thing turns this way. So as it turns this way, it's going to create a magnetic field to the right. If I poke my fingers to the right from the left-hand side of it and grab the bottom, I would see that the current would be going into the page at the bottom and then coming up behind the page and then coming out of the page at the top and then going down. So I would see basically if I was looking this way at the ring, I would see the current being counterclockwise. So again, y'all have this video. Y'all can go back and rewind it and all that good stuff. But that's a pretty exhaustive explanation of how Lenz's law is used. I hope that helps you. There's some other ones right here. Exercise B. Every time you get a chance, just do it. Okay, just predict it every time. All right, let's look at example 29.5. And you can see it right here. It says 100 loop square coil of wire of side L equal 5.00 centimeters is and total resistance R equals 100 ohms is positioned perpendicularly to a uniform magnetic field of B equals 0.600 Tesla as shown in figure 2911. It is quickly excuse me, pulled from the field at a constant speed, moving perpendicular to the magnetic field B to a region where B abruptly drops to zero. At T equals zero, the right edge of the coil is at the edge of the field. It takes 0.100 seconds for the whole coil to reach the field-free region. Determine A, the rate of change of flux through the loop of the coil, and B, the total EMF and current induced in the 100 loop coil. C, how much energy is dissipated in the coil, and D, what is the average force required? So that's the problem we're going to try to solve. I'm going to use a whole other page to do that, and I'm going to go ahead and stop this share and start sharing my iPad screen with you again. Hopefully it won't take so long. Anybody have any questions before we move on? That should pop up any minute now. I did see a question on the chat, so I will do my best to check that out and say, oh, here it is. Isn't this how old variable reluctance wheel speed sensors in vehicles work? Yes, you can use that. In fact, I worked for a company in Elizabeth City that's called Motion Sensors. It's a small company that does a really big job for a lot of places all around the world. But they basically have little devices that make solenoid. They're basically solenoids, and they run a current through it. And by that current running through it, it creates a magnetic field that propagates outward. Well, if you stick that little probe next to, let's say, an iron disc that is sort of like the disc that would be a wheel of a train, for instance, then what you can do is you can monitor how that magnetic field changes because how the current changes through it, and you can basically use that as an odometer for telling you how many times the wheel rotates, and that can be used as a speedometer as well as a count of turbine blade turns, all sorts of stuff like that. Okay, someone asked about the two separate times. So yes, you have to have two scheduled appointments. I've given you a list of times that I'll be available for the face-to-face test, and I'm going to give you a list of times that I'll be available for the final exam, which is also face-to-face. But you will have to have, if you're not using those resources and you're not using any of the Zoom resources that I offer, then you're going to have to schedule testing center testing. And I've given you a copious amount of time. Like today was the first day you could have actually taken the face-to-face test three, and I think I'm allowing you all the way until Tuesday of next week to do that. And then you're allowed all the way until Friday, or excuse me, till May 4th, which is a Monday. And you have to have it finished by noon on Monday, May 4th, but you have until then to do the final exam. Okay. So again, going back to example 29.5, just as soon as I find my, oh, there it is. So example 29.5, what we were given was L is equal to 5.00 centimeters. We were given R is equal to 100 ohms. We were also given N is equal to 100 loops. And we're given B is equal to 0.600 Tesla. And we're told that it takes delta t equals 0.100 seconds for the loop to go from the right edge lining up with the right edge of the magnetic field until the left edge lines up with it so that it has no flux whatsoever. So let me draw that real quick. What we're going to have here is, let's say, this 3 by 3 square of n loops. And this 3 by 3 square is submerged in a magnetic field that dies right along this green line. And it's a uniform magnetic field and it points into the page. So what you can see is we can imagine this thing moving with a velocity v equals question mark, but we do know that the length from here to here is L, and the length from here to here is also L. And we know that V is equal to, remember, it's moving at a constant rate. It said specifically uh, it is quickly pulled from the field at a constant speed. So if we calculate the average speed, we'll calculate the speed. So the average speed, V bar, is just V, and that's L over delta T. And that L, of course, is 5.00 times 10 to the negative 2 meters divided by 0.100 seconds. So that gives us 5.00 times 10 to the negative 1 meters per second is the velocity. Now, what we can look at is the magnetic flux. In this case, we don't have to do an integral because the magnetic field is pretty much uniform, its direction is uniform, and the area is all the same. But the problem is the area is actually changing. So it's going to be the magnetic field, B, times the height, which is L. We're actually calculating the area, by the way. Uh, so the L is part of the area, and right now the total area is L squared, right? But as time goes on, that area is going to get smaller. So I'm subtracting from that the distance V times T because if you wait a time t, then it will have moved the distance v times t, and that v times t is the length of the part of the rectangle that's no longer in the magnetic field, so it should be subtracted from it. So that's what our actual magnetic field flux looks like. So I've got b times l squared minus b times l times v times t. So if I want to know delta phi b over delta t, and that's quite possibly the worst phi symbol I've ever drawn in my life, and I just can't leave it, which I wish I could, but anyways, so delta phi b over delta t is basically going to be, hey, I'm going to take and try to figure out what this is. I'm going to, in this case, since I've written it this way, I can easily go ahead and treat this like a derivative, and I can say d phi b over dt is equal to d by dt of bl squared minus b times l times v times t. And you can see the derivative of bl squared is 0. The derivative of blvt is just negative blv. So I'm going to get negative b times l times v is the d phi b over dt. And that means that E, the induced EMF, is negative n d phi b over dt, which becomes positive. Oops. It becomes positive n times b times l times v. Now, that's the expression I just derived for this particular problem, but we're going to use that over and over again. Anytime you have something of length L moving through a magnetic field such that the magnetic field is perpendicular to that length L, then the induced current is always going to be B times L times V. And if you have N loops, it's going to be N times BLV. So keep that in mind. That's going to come up over and over again. They're going to say things like, hey, aircraft is flying in a place where the magnetic field points straight up and the tips of the wings are 70 meters apart. So if it's moving at 700 kilometers per hour, what's the induced voltage from one side to the other? And you would just use this with the N being 1. Okay. So that's something to think about. In this case, they're first asking for part A, and part A wants to know the rate of change of flux. So d phi b over dt is the rate of change of flux. And of course, we've discovered that that is actually negative. Well, actually, yeah, we can call it negative. They're looking for a rate. They don't necessarily, I guess it has to be negative because it is decreasing. So I'm just going to say negative BLV. Okay. So that's the change, the rate of change of the magnetic flux for part A. For part B, they want the total EMF and the current induced. For the EMF, we get positive N times B times L times V, which equals 100, because there's 100 loops, times 0.600 Tesla times 5.00 times 10 to the negative 2 meters times the velocity, which is 5.00 times 10 to the negative 1 meters per second. And that gives us E induced is equal to 100 times zero point 0.6 times 5 times 10 to the negative 2 times 5 times 10 to the negative 1, and that gives me 1.5 volts. Now, we had that good to 3 sig figs, so I went ahead and just showed you off. I showed you 4 digits, so there shouldn't, we always have an extra digit to use. So that's the induced EMF. Now, the induced current would be given by E equals IR. So E is equal to I times R means I is equal to, in this case, we're going to take 1.500 volts and divide it by 100 ohms. And from that, we can see that I is going to equal 1.500 times 10 to the negative 2 amps, which you could also write as 0.01500 amps, like that. So it's around 15 milliamps. Anybody have any questions on that? All right, for part C, they want to know how much energy is dissipated. So, how much, oops, So how much energy is dissipated? Well, P is equal to IV is a way we can work on this. So I'm going to use that, and that'll give me the amount of joules per second, i.e. watts. So with that in mind, all I have to do is take and write P equals I times V. But then to get the energy, I have to multiply that by time. So remember, P is equal to energy over time. So that means the energy that's actually dissipated is I times V times T. And we knew specifically that the time that it went from being completely immersed in the magnetic field to nothing is the 0.100 seconds. So we can go ahead and use that math. That's going to be 1.5 times 10 to the negative 2 times 10 to the negative 2 amps times V, which is 1.500 volts, and then times T, which is 0.100 seconds. And with that in mind, we got 1.5 times 10 to the negative 2 times 1.5 times zero point 0.1, and that gives me 2.25, 2.250 times 10 to the negative 3 joules. That's how much energy is dissipated in this little process. Okay. Now, for part D, they want to know what is the average force required to do this. So, what you want to think about is, for starters, what's going to happen to each of these sides of the loop as it's moved through a magnetic field. So, for instance, if we look at the top, the current induced, we've got to figure out for starters which way the induced current will be. So, can anybody, actually, this would be a good question to ask you guys. How much current, or which direction is the current induced in this loop of wire? The loop of wire is moving to the right. Your answers are counterclockwise or clockwise. Okay. So what do y'all think for part D? Which direction? And even though that's only a small part of part D, but we got to know which direction the current is before we can figure out which direction the forces are. Anyone? Someone said counterclockwise. So we know that the flux is decreasing because the area is getting smaller. The area in the magnetic field is getting smaller. So it's going to try to strengthen that magnetic field to make the flux get back where it was, even though it can't, but it's going to try. So we're going to create a magnetic field going in through the middle. So if I put my fingers in through the middle and then grab that bottom wire, I see my right thumb is pointing to the left, and that means it's going to be actually clockwise. Sorry about that, Alex. So this one will be clockwise. I'm going to draw that by drawing the current right here, right here, right here, and right there. Now I want to examine that top part right here. Remember F is equal to IL cross B. Remember that? F is equal to IL cross B. Well, for that top wire, IL is to the right and B is into the board. So I've got like that, and that tells me that the force on the top wire is going to be upward. So I'm going to write F in black is upward. Now, if we look at the bottom wire, I've got IL pointing that way. And again, I'm using my hand like this. So IL is my index finger. Now I've got to turn my middle finger to point in the direction of the magnetic field. That's like that. That means the force on the bottom wire is going to be in the downward direction. And in fact, the magnetic field and the length of the wire and the current going through the wire are all the same. So those two forces should cancel each other out. Now, right now, the left-hand side, if it had a current going through it, the left-hand side would actually experience a force, and that would be IL to the right. But as soon as we start moving, that right-hand side's not in the magnetic field anywhere, so that right-hand side's not going to feel a force at all. The left-hand side, on the other hand, has IL going up, turning my middle finger so that it points in the direction of B, tells me that the force on this left side is going to be to the left. So it's actually going to take some force for me to pull it out. So that's one thing just to tell me. But now what I can do is I can realize that energy is equivalent to work. So I can say E equals the work done. So if we imagine the actual energy dissipated is the energy put into the system by doing work, we could actually say work is equal to the average force times the change in position, delta x. So if that's the case, then we'd find that the uh, average position or the average force would be the energy divided by delta x. Or we could also use F equals IL cross B. I'm going to do that one. So we know what the current is. In fact, the force is going to be I, which is 1.50 times 10 to the negative 2 amps, times the length, which is 5.00 times 10 to the negative 2 meters, times the magnetic field, which is 0.600 Tesla, if I remember correctly. Yep, that's right. And we got to remember that, in fact, it's not one wire, it's in wires. So I've got to multiply that by 100 because it's in wires. It's not just one wire going with the current going in the upward direction, it's in of them. So if I do all this math, I can say 1.5 times 10 to the negative 2 times 5 times 10 to the negative 2 times zero point 0.6 times 100, and that gives me a force equal to 0.0450 newtons. So that's 4.5 times 10 to the negative 2 newtons. Not to the right number of sig figs, but it was to the right number when I did it at first. So that's the force. Anybody have any questions on that? So you notice you could have also done it this way, and if you chose to do it this way, it would have been 2.25 times 10 to the negative 3 joules, which is what we had for the energy. And the L, of course, was 5.00 times 10 to the negative 2 meters. And lo and behold, that turns out to be 0.04500 newtons as well. So both ways actually would have worked in that case. Anybody have any questions on that? All right. Well, I want to answer your questions. I saw that there was a lot more questions, so I only got 2 minutes left. I'm gonna make another video, a couple more videos, sometime between now and this weekend, and that's gonna fill in some of the gaps for chapter 29. We're gonna do a quick example or two from chapter 30, and then we'll do that on Wednesday, or excuse me, we'll do that on Thursday, and we're also gonna do some more examples in this, and then we're gonna just mention a couple things in chapter 31, and that's all you're going to be responsible for. And I'm probably not even going to ask any questions on 31. I just can't, I don't feel right about not exposing you a little bit to chapter 31. So I'm looking at these questions that said, isn't this other, oh, no, that's a different one. Isn't this isn't related to material. No, from the announcement you posted a couple of days ago, I thought the final exam was going to be due a bit later. The latest the final exam can be due is May 4th, because that's the day I have to turn my grades in. The last day of classes is May 4th, and I'm giving y'all up until, like I said, noon on May 4th to complete that. Uh, with exams. Nope. Okay. Yeah, and all I've given you so far is the face-to-face test. My face-to-face class are taking their tests tomorrow. So that's why tomorrow is a time where you can come in and have it proctored by me at class. But if you want to wait, because I do allow you to take it as late as Tuesday of next week, then you can do one of my Zoom sessions, or you can just book something at a testing center. Again, if you use one of our testing centers at one of our campuses, it'll be free, but you do have to make an appointment and some stuff like that. And you're also supposed to have let me know last night where you're going to have your test at, because I'm not sending the test out until I know people are taking it. That being said, I'm probably going to send it out tonight because I had to make it for tomorrow's. Uh, and I think that's about it. So remember your face-to-face test according to the announcements. Let me look at that. I want to read that to everybody so it'll be on this recorded form real quick. So I'm opening up the announcements for your course, and I'm looking at the face-to-face test 3 and final exam. It said decided to limit the face-to-face test to chapter 17 through 29, mostly on 27, 28, and 29. Actually, I just realized, holy crap, this is just chapter 29. So obviously, your face-to-face test can't have any more than this level of problem that I just did right here. So I'm not going to go any further in this on the face-to-face version of the test that I made. In fact, I got to take one question out. I've already made it, and there's one question I got to take out. But this is a fair approximation of chapter 29, so I don't have a problem with that. So it says the final face-to-face tests. Remember the final exams also proctored and as comprehensive, but it can be completed by you as early as yesterday, but no later than 11:59 on Tuesday, the 28th of April. So a week from today is the last time you can take it. So you've got to schedule an appointment at a testing center, or you got to attend one of my Zoom meetings, or you got to come to class tomorrow on campus to have me proctor it. That's sort of your only choices. I did say my Zoom proctoring times are Friday, April the 24th at 1 p.m., Saturday, April 25th at 10 a.m., Tuesday, April 28th at noon, and Tuesday, April 28th at 7 p.m. My in-class proctoring times are tomorrow at noon to 1:30, or 12:20 to 1:50, or 1:50 to 3:10, or 2 p.m. to 3:30. All of those are likely to be in JC13. Each of you must email me your chosen testing time by 8 a.m. on Tuesday, April the 25th, which obviously some people didn't do, but that's okay. Do it now, and that'll help me. So make sure y'all do that. And that's it. Anybody have any questions? I'm going to be here till the last person leaves in case anybody does have any questions, but you are all free to go. Make sure you chat at me your first and last name if you haven't done so already. And here's that announcement that I was just reading in case y'all wanted to get a last minute look at it. Remember, I did say the final exam has to be completed by noon on May 4th.
So since I have a different schedule than your online class,
Mm-hmm. You can do either one.
um, okay,
Yeah, you
but
can
I'm
choose to
okay.
do the one with the online classes, or you can come do mine tomorrow. It doesn't matter too much, and you're actually going to get a different version. So even if you talk to someone, which I don't recommend them doing, you wouldn't be getting that much of an advantage.
Okay. And I had another question.
Mhm.
Is the Gauss and capacitance, I think, is it gonna be on the test again?
Yes, that's the whole reason that I gave it on the last test, and the reason
Right.
why I gave you that extra credit. So yeah, I could do the Gauss paradigm where I ask you to use Gauss's law to calculate the electric field, then figure out the electric field between two parts of a capacitor, then use V equals negative integral E dot dl to calculate the voltage difference, and then use C equals Q over V to calculate the capacitance. That is very much a real problem. We did it on your test, the last face-to-face test. I did it with the infinitely large plates, flat plates, but it could be the cylinder, coaxial cable, or it could be these spherical capacitor. All of those are fair game.
Awesome. Okay. Sounds good. See you
Uh,
tomorrow then.
See ya, Anahi.
Bye.
Anybody else?
So is the final exam, is that also one that we can do with the testing center?
Yes, you can do it at a testing center. You can do it with me. You can do it on a tutor at a Zoom session with me. All of those are fair games, but it just has to be proctored. That's the main thing.
Okay. All right. Thank you.
All right. See you, Giovanni.
Have a good night.
You too. How about you, Alex? What's going on, bud?
Hello. I just wanted to get a conceptual question out the way, and it was
Hmm.
related to the problem that you did with the square with the n number of wires wrapped around it. So the
Okay.
force that's being applied towards the left-hand side, that's going to be a constant force until that coil of wire exits the magnetic field, right?
Right.
Okay.
Yeah, it pretty
Uh,
much stays the same way, mainly because conservation of charge wouldn't allow it to do anything. So even though there's that one side's immediately going to be out of the magnetic field, and then part of the top and bottom is going to be out immediately, it's still going to maintain that current going through it. That's why we do examples like a 70-meter wide wingspan could actually develop a voltage difference between the tips because it just has to have one part for it to develop a voltage difference. It doesn't have to have a closed loop, in other words.
okay, that makes sense. And I guess I was also thinking ahead. And if instead of a square, it would
Hmm.
have been a triangle, and the point would be on the left-hand side. Would the force be a function of time then, because the force is constantly changing as you pull it out?
Yeah. What were you saying the initial part? Why did you think it came out to be a varying force? What was it?
Um,
I got
so
sidetracked in my mind, so I ended up not listening to a part of your question.
you're
I'm sorry.
okay. Um, Here, I think I can use the pen on this. Oop,
Yep,
my bad. Here, I don't
that's
think
okay.
I can.
Write on it all you want.
There you go. So it would be like this, and then the x's will be on this side,
Okay, gotcha.
and then the velocity will go this way. Here we go.
Gotcha. So you're talking
So
like a triangular loop instead of a rectangular loop?
yes,
Okay.
and can I zoom in on this thing? No, it's gonna draw. Dang it. Um.
Yeah,
So
I'm not
as
sure if that would
mhm.
actually cause it the force to vary. It might have. No, I'm not sure it would even cause the force to vary in that way. You'd have to have for it to vary. You'd have to have some way to have the magnetic field varying or something. I
Oh,
don't think
okay.
that. Yeah, because I suspect you could take that rectangle and tilt it like that and pull it through, and you still get the same current going through it.
Oh, that's kind of cool. Okay.
Yeah, it's worth trying experimentally. Otherwise, I just have to do a calculation to see. But anyways, yeah, that's what it's going to be in general. Don't forget to let me know what day you're planning on taking the test, because now I've got to realize because we got behind on chapter 29, I have to limit the tests that I'm giving you face to face, folks. So I got to make sure I don't go past any of the material I covered today, and even that I don't feel that good about. So it's not going to count much.
Oh, I got you. Yeah, no, I I misread it and I looked at it today because I thought it said 8 p.m. instead of 8 a.m.
Oh, gotcha.
After work, I was like, okay, cool. And I
I
was like,
thought
oh
it said
no.
midnight by tonight, so you did better than me.
Oh, no. But I sent you the email. I
Okay.
think at around 4, but I think it's all good.
Oh yeah, yeah, I did see your email come through. I remember seeing it earlier today.
Okay, well, thank you so much.
All right, thanks, Alex. Have a good one. Let me know if I can help you with anything.
I got you. All right, I'll
All
catch you
right.
later.
See you, bud. Have a good one. Bye, everybody. Look, Monday shirt, and it's not Monday. That's because I'm lazy.